In this video, we'll develop the general concept of a mathematical model. After studying this video, you should be able to identify mathematical models that you used in various engineering and science disciplines in previous courses. You should also be able to describe any mathematical model in generalized terms that are independent of its application. So what do we mean when we use the term mathematical model? A mathematical model is any equation or system of equations that relate different aspects of a physical, biological, or engineering system or process. A model may be as simple as a single linear algebraic equation or as complex as a system of nonlinear partial differential equations, and anything in between. A model may be developed from fundamental scientific first principles, or that model might be experimentally derived using empirical relationships. Or it might be somewhere in between, or some combination of these two approaches. Engineers and scientists use models for the following. They use them to understand the relationships between different parameters of a system or a process. They also use them to make design decisions to optimize the performance of an engineered object or system. Models are also useful to communicate observations and insights to other people working in your same discipline or scientific community. And we use those to develop and test new models that might give better results or more accurate predictions. So here's some examples you should be familiar with from physics. Newton's second law is a simple mathematical model relating force, mass, and acceleration. If we combine that with definitions of acceleration and velocity, we can come up with another statement of Newton's second law. Same basic model, but expressed a little bit differently. In the first case, F equals ma, we have a simple algebraic relationship between acceleration, mass, and force. In the second example, we have F equals m times the second derivative of x, or position, with respect to time, and that is now a simple differential equation. We can use that to derive other mathematical models, as you probably saw in your physics classes, and maybe dynamics if you've taken dynamics. One, for constant acceleration, we could solve for a is F over m. If that force and mass are constant, we can derive the constant acceleration kinematics equations, one of which calculates the position of a particle as a function of time. Another approach is, or another result that we often use, is the spring mass oscillator vibration model, where we've broken out two specific forces, a damping force and a spring force, from the force model to write a second order differential equation for the position x as a function of time. Here's a couple more examples. Here's another second order differential equation model for a series RLC circuit. You may not be familiar with this idea if you haven't encountered a circuits course before, but for now just think of RLC circuits are electrical models, a circuit model of an electrical system where L is the inductance of the system, R is the resistance of the system, and C is the capacitance of the system, and they're generally all constants. Now you can solve that differential equation for the voltage as a function of time under certain conditions, and the result is this model, which is again, an algebraic model derived from a differential equation solution. Very similar to what we had for our kinematics equation here, an algebraic model derived from a differential equation. Here's a similar model I just threw in here just to see how things are common across disciplines. This is a decay model for population of two biological organisms, which we would call A and B, and looking at their total population of those contaminants in a lake and how that decays over time. So what do these models have in common? Well, first of all, let's look at these two, the kinematics model and the population model. We see in both of these cases we have some independent variable x is some function of time. And here we have an independent variable p is some function of time. So time is the independent variable in both cases. Both models also involve an algebraic mathematical relationship. In the case of the kinematics model, we have a quadratic polynomial or parabola. In the case of the population model, we have an exponential model. Actually, a linear combination of two exponentials. And then both models have other variables in the model that represent physical characteristics of the system. For example, the initial velocity in the kinematics model, or the constant acceleration of the particle in the kinematics model, or in this case we have the initial concentration of organism A in the population decay model, and then the two decay rates, Ka and Kb. So these are two different models from very different areas of science and engineering. However, they do have a lot in common. Let's look at a couple others. Here is the RLC circuit model and the spring mass oscillator model. Again, in both cases, time is the independent variable. However, in this case, since these are differential equations, the models represent relationships between a dependent variable and its derivatives. So V, we can think about this as V, if that's for the RLC circuit, V is some function of dV dt first and second derivatives, as well as t if there's a functional relationship of t. Again, both models include other variables that represent characteristics of the system. So in this case we have R, L, and C for the RLC circuit model. These are represent the electrical characteristics. And in the circuit, or in the spring mass oscillator model, we have M, C, and K are mechanical characteristics of that system. K being the spring constant, C being the damping coefficient, and M being the mass. And both of these models, they allow us to model external influences with the forcing function. And this is just some function of t that we can use to model some external thing. For example, thinking about the spring mass oscillator, maybe we have some motor that is acting on that vibrating system, or if we're using a spring mass oscillator model to model a building in an earthquake, maybe that is modeling an earthquake. So let's see if we can generalize this and make some conclusions about mathematical models. So in general, a mathematical model is going to consist of a dependent variable and one or more of the following. a dependent variable, or sorry, 0 or more independent variables, 1 or more parameters that reflect physical characteristics of the system or process, and maybe a forcing function that models external influences on the system. And importantly, that mathematical model will include some sort of functional relationship between the dependent variable and the other aspects of the model. So let's take a look back at the models we've identified as examples and see how we can classify the variables into those categories. So first of all, with Newton's second law, we actually should remember that that force F is not necessarily constant, and that actually is our forcing function. And in general, F could be some function of time, position, velocity, etc. The mass would be a parameter, and the acceleration would be our dependent variable. These two definitions aren't really mathematical models so much as they are just definitions, so we won't worry about those. Now, in our applying those definitions to take our Newton's second law model one step further, here we still have F as a forcing function and M as a parameter, but now we've written this in terms of a dependent variable X and an independent variable time. So in our first model for Newton's second law, we had no independent variable. There was no time or space variable that served as our independent variable. In our differential equation model for Newton's second law, we do have an independent variable, time. And now if we look at two solutions to that we were talking about, one for constant acceleration and one broadening the model for a spring mass, or applying the model to a spring mass oscillator, we can again identify in the constant acceleration model, we have several parameters. We have x naught, v naught, and a, in this case, are all parameters that describe the physical characteristics of that system. And you may say, well, wait a minute, a was just a dependent variable in Newton's second law, but now it's a parameter? And one thing to see here is whether something is a parameter or a dependent or independent variable or a forcing function always depends on the context of the model. Remember that this whole model for constant acceleration kinematics started with some assumption that the acceleration is a constant. And if the acceleration is a constant, suddenly that becomes a physical characteristic of that system, and thus a parameter. And now we have an independent variable again in this case with time, and our dependent variable again is x. Similarly, for the vibration model, x is again our dependent variable. Time is our independent variable. And we have some parameters. M, C, and K are parameters. And F is a forcing function. So hopefully you can go back and take a look at models that you've seen in previous courses and think about them in this kind of abstract sense of what is the independent variable, what is the dependent variable, are there any parameters in the model, and what, if any, is the forcing function. So why does this matter? Well, it's really important to be able to generalize the idea of a mathematical model. In this course, we're focusing on scientific computing using MATLAB and numerical methods. So both of these are MATLAB and the numerical methods that we'll use in MATLAB. These are tools that we use to work with and analyze mathematical models and study them and see how they behave under different situations. And as we develop these tools, it's really important that we can develop them independently of the specific problems that they'll be applied to. So we want to understand the commonality of models from different disciplines, and that allows us to develop more broadly applicable tools. So instead of thinking, how are we going to develop a model to work for the spring mass oscillator problem, we can think about how are we going to develop a model that handles a dependent variable, 0 or more independent variables, 1 or more parameters, and that accounts, where applicable, a forcing function, if that might be part of the mix. And so we'll use that generic form of a mathematical model that we just talked about throughout the course in order to accomplish this.